Welcome back for the online class. Now, in today's class, we will discuss on wavelets and multi-resolution processing. Before we discuss, now let us know about the transformation. As we know, we have studied on Fourier transform, in which it will convert from the time domain to the frequency domain. Means the operation will be performed with respect to the frequency. Now, here the basic operation involved for the wavelet transform is making it even easier for the operation of compression, for the transmission, and for analyze the many images. Okay. The basis functions are sinusoids, in which wavelet transforms are based on small waves called wavelets, in which it is a variation of frequency or with respect to the image content. Now, if you are looking into the history of the wavelets, it is the foundation of a powerful new approach for the signal processing and analysis called multi-resolution theory, that is the operations involved for the multi-resolution images. We will see what you mean by exactly the multi-resolution in an image. Now I hope you can see the image, in which the image, when you observe the image, image has got like a, in the image the various contents, leaves, and there is like a bars, and we have like a mud, and various components are involved here. When you observe on an image, the image, different components have a different color or different grayscale. When we are considered it's a histogram, we can see there is like the histogram of this, there is a bar, it will be look like this. The histogram, histogram of this one, it will be like this. The histogram of this full image, it will be like this. And the histogram corresponding for this one will be like this. The conclusion behind this one is that in an image, it has got like a various components. Each component it has its own color. When we consider there is a box, there is like a set of pixels of the image. We need to be operate on like a histogram. It will give a different like a histogram for the corresponding set of pixels. Since when we consider there is a histogram of an image, it will be directly indicate the time domain. Means we can see there is a variation will be different for different images. Since if you consider it is in terms of like a time domain, there is like a various time durations. Means what is varying here? The intensity of the image is varying. The intensity will be directly indicated to its frequency, since the variation of frequency with respect to the time. Now I took it to the with respect to the time, it will be various with respect to the component of the image. What is varying here? Frequency will be varying. The frequency of what? The frequency of an image. Particular pixel images. That will be varying. Means in the image itself, different component give a different resolution. So in order to operate for the image analysis, we need to be considered a component by component, and we have to analyze with respect to its frequency. That is what the basic operation to be performed. In which the variation of frequency in the image, that will directly indicate for the wavelet transform. I hope you can see. Hope the image I have shown previously, in which some of the image pixels has got brighter pixels, some pixels will be having a lighter pixels. In between this, the depends on a various image content, the pixel color will be changing. Okay, now it will be marked in the form of a square box. Okay, and we took as its histogram. Okay, now when we draw, it is in terms of the variation from variation from high to low or low to high. Okay, it will be look in the form of a pyramid. Okay, I hope it is visible for you. Okay, it is in terms of a pyramid. This pyramid indicates the change in resolution, means sum of the pixels. Okay, the sum of the pixels, okay, what I have considered at the level 0, okay, indicated with a 1 by 1. Okay, the size of the image I have considered as a 1 by 1. Okay, during this 1 by 1, the pixels has what a set of pixels, it will indicated with a certain color. Okay, and certain color that will be drawn or that will be converted in the form of a frequency, and we need to analyze. Okay, now just now I told, if I consider a different part in an image and the set of pixel I took it as a 2 by 2, means how many pixels will be having here? 2 by 2, 4 pixels will be coming here. Okay, and it will be in the form in level 1. These pixels might be having a different color, and we need to be analyze its frequency with respect to frequency, because the frequency will be analyzing. Okay, that is what I shown with the previously in terms of a histogram. Okay, now same way, if you go for a 4 by 4, means now the box size is getting increased. 4 by 4, total how many pixels will be there? 16 pixels. All the 16 pixels indicated with a different color, and that color, it will be, okay, if I take it it's in terms of a graph with respect to the frequency, and we need to analyze. So how it will be increasing? Let is 4 by 4, 8 by 8, 16 by 16, 32 by 32, until what? Till you find a bigger pixels, that is the bigger box pixels, for the n by n pixels up to 256. If a image will be 256 by 256, okay, it is divided in the form of a boxes, and we are analyzing it. Okay, and this level, what we call, is a pyramid. Okay, and the analysis is with respect to the variation of the frequency. If I take 1 by 1, 2 by 2, 4 by 4, okay, definitely the pixel size will be, more number of pixels will be increasing. The change in color is also changing. It is increasing or a decreasing. Hope you understood this. I am using a word increasing or the decreasing. Okay, and we need to analyze. Okay, now just now I said, if the frequency will be increasing, okay, okay, we know that in the communication we use a sampling theory or a sampling concept. The sampling concept is nothing but, okay, f, okay, there is a sampling fs, there is a sampling frequency has to be greater than 2 fm, means fm will be the maximum frequency of the corresponding box. Okay, means it has to be greater than equal to, okay, greater than equal to 2 fm. Okay, this is what the sampling theory. Okay, so similarly, okay, just now I said the previously we are increasing or a decreasing. If the frequency will be increasing, no matter that we are obeying the sampling theory. Look at this one. Okay, means if the frequency is increasing, okay, there is a 2 fm will be maintained. Sampling concept. Okay, if the frequency will be decreasing, okay, now if I go from bottom to top, okay, let us take that n by 2 by 2, n by 2 into n by 2. If I going down, okay, as good as we are doing with a down sampling. A down sampling in the sense the frequency will be decreasing. Okay, it is decreasing in the sense you should not disobey the sampling theorem. You need to be take into consideration that, okay, that is fs has to be twice the greater than fm. Okay, if it is disobey, then you may not reconstruct your original image. That is very much strict condition. Okay, so since Okay, if I go from from top to bottom in the pyramid, the frequency, there is a upsampling. I call it as a upsampling. Similarly, if you're going from bottom to top in the pyramid, we are downsampling. Okay, in the downsampling, you make sure that you should not disobey the sampling theorem. Right. Okay, this is what the pyramidical approach what we are applying for the image. Okay, it is based on the a frequency. We call it as a wavelet transform. Okay, now I hope you can see. Okay, in the diagram. Okay, we are just given with downsamplers. If you are going from bottom to top, upsamplers from top to bottom. That is from 1 by 1, 2 by 2, 4 by 4. Anyway, the more number of pixels will be increasing. So then you are always obeying the sampling theorem. Okay. Now this is what it is given here, levels. Okay. Now if I consider in the left side, okay, level G, okay, level J, any level, that is a 1 by 1 level. You can start from 2 by 2, you can start from 4 by 4. Okay, level J, approximation filter means the image will be filtered by using low frequency or high frequency filter. Okay, and make sure that, okay, if it is either will be in the downsampler or it will be in upsampler, you should be having two L levels. Okay, and which level you are operating, that has to be maintained, and it is given to the approximation for the level J minus 1. Similarly, okay, if it is going for an interpolation, that is for upsampler, we need to follow the path like this. Okay, that is for upsampler we are increasing, that is a plus sign. Okay, for the downsampler it will be decreasing, there is a minus what we are given. Okay, you are not decreasing. Okay, you are not removing the samples. Okay, if you remove the samples, then you might have lose the content of the image. That should not happen. We need to be just in the downsampler. Okay, there is a simple concept is that by adding a zeros, okay, we are maintaining the sampling theorem. Okay, I hope you understood this one. Okay, now the very much popular techniques, okay, you might have seen in the signal processing, it is very much essential for your wavelet transform is signaling. There is a timing signal diagrams. Okay, now I hope you can see it is a h1 of n. It is started. Okay, it is given at the h of 0. H of 0, this is the signal. H of 1, we have a sample. We have h of 2, we have negative sample, and h of 3, we have a negative sample. Okay, now there is a various techniques how we can operate here. If I took it here, it's in the second diagram minus h1 of n means all these positive samples becomes a negative and the negative samples become a positive. This is just applying a negativity. Minus to this one, minus to this one. What if these are the positive signals here? If I apply a minus here, all will become a negative, and all negative samples become a positive at the same time period. Hope you understood this one. At the same time period, all positive samples become negative and the negative samples become a positive in the first diagram. Okay, in this diagram. Similarly, okay, I hope you can see in the third diagram, h1 of minus n. h1 of minus n in the sense it is a mirror image. We took it as a mirror of the original image. What is my original image? This is your original image. What is the signal you have? H of 0. Okay, mirror of this one, replicate it. Okay, and h of 0 we have a positive. Okay, now h of 0, this is the immer here. H of 1 we have this signal, and h of minus 1, there's a minus 1. Okay, we get here. Okay, h of 2 we have this signal. H of minus 2, it has to go like this. H of 3, this one. H of minus 3. Okay, likewise it will be indicated for the third diagram. Okay, I hope you understood the frequency, there is a timing diagram here. Okay. Now in the fourth one, h of 4 of n is equal to h1 k minus 1 minus n. Okay. Now let us take that k will be started from 0. Okay. Now in this fourth one, okay, when applying here h1 of k minus 1 minus n, okay. Now it is not like a mirror image. It is previously all in the third diagram, all the samples will be exactly replicated at the other end. There is a second quadrant. Now in the same quadrant, in the fourth one, okay, just you replicate with the same quadrant. Okay. Now, okay, look at here. This sample, okay, it is at the h of 3. Now it will be becomes at h of 0. H of 2, this will be at h of 2. Okay. Now, okay, for a minute. Okay. Now, okay. In the sixth diagram, okay, whatever you obtained, okay, whatever you obtained here, okay, in the fifth one, you just replicate here. Means you just reverse it, flip it, okay, flipping in the sense, okay, this is how I got here, okay. Now this negative, okay, because minus 1 raised to n h1 in h1 of k minus 1 minus n, means this is negative. When you reverse it at this point, okay, you will find a negative sample, and this sample will go to the corresponding positive. Means now here negative, this will become a positive here. Similarly, this will be flipped here. Now it is negative, this will becomes a positive here. Now this is a positive here. Now it will become a positive. This becomes a negative for the sixth diagram. Okay. I hope you'll find just flip for the fifth diagram. Okay. Flip the fifth diagram, you will find h6 of n, that is a minus 1 raised to n into h1 of k minus 1 minus n. Okay. And okay, now this is like what the diagrammatic approach, what you can see, what you can get it here. This is the basic operations we will carry it for the wavelet transform, okay, with respect to the image, okay, for the downsampling and the upsampling, okay, because when we are performing like time shifting operations with respect to the image, that is with respect to the pixel content, okay, the frequency domain, especially for the frequency domain, we may go with like a h1 of n, h1 of minus h1 of n, minus h1 of minus n, okay, h1 of k minus 1 minus n, okay, there is a value of k will be depends, it will be changed, either it will be 0, okay, it will be 1, and depends on the value. And for the minus 1 raised to n h1 of n, minus 1 raised to n h1 of k minus 1 minus n, okay, with all the diagrams, all the corresponding, all the five diagrams are drawn with respect to the basic first diagram, that is h1 of n, and the samples will be given at h of 0, h1, h of 1, h of 2, h of 3. Okay, I hope you understood, and this is very much essential for your wavelet transform to carry your multi-resolution operations. Okay, since this is about the basic component is required for the wavelet transform operations. Thank you.